hydrogen bond. This hydrogen bond belongs to the category of van der Waals forces of attraction because it's not a chemical bond. Actually, here it has certain ionic characters because in hydrogen bond, the force of attractions are electrostatic force of attractions. Only hydrogen atom can form this type of bond. That's why this bond is known as hydrogen bond. Except hydrogen atom, no other atom are able to form this type of bonds. Exclusively hydrogen. And hydrogen also, when it was bonded with a covalent bond with a high electronegative and small size atoms like oxygen, fluorine and nitrogen. That is, the molecules which are having a bond with hydrogen, where hydrogen is bonded with atoms of small size and high electronegative. Small size and high electronegative elements, they are oxygen, fluorine and nitrogen. These are the three elements where the compounds where hydrogen is bonded with any one of these elements. In such molecules, we can observe hydrogen bond. That's why this bond is specially called as hydrogen bond. When hydrogen is bonded with high electronegative and small size atoms like oxygen, hydrogen and fluorine. Here we have a molecule in which hydrogen is bonded with oxygen. Herein, this is a polar covalent bond where hydrogen will have partial positive charge and it will have partial negative charge. Now, the hydrogen which is having a partial positively charged hydrogen, when it is in contact or nearer to a partially negatively charged atom, other than it was bonded with a covalent bond. In such cases, a weak electrostatic force of attraction will arise between hydrogen and oxygen of other molecule. This type of bond is known as hydrogen bond. And in turn, this hydrogen will form another bond with another oxygen atom of another H2O molecule. And this hydrogen will form hydrogen bond with another So, by that way, each H2O molecule at an average they form two hydrogen bonds with adjacent H2O molecules. This type of bond is formed between two different molecules. Such hydrogen bond is said to be intermolecular hydrogen bond. Intermolecular hydrogen bond. If hydrogen bond is formed between two different molecules, such hydrogen bond is said to be intermolecular hydrogen bond. There is another type of hydrogen bond which is formed in between the two groups of a same molecule. Such hydrogen bond is said to be intramolecular hydrogen bond. Intramolecular hydrogen bond. For example, salicylaldehyde. Now we have a partial positively charged hydrogen which is bonded to oxygen, another partial negatively charged oxygen belonging to the same molecule. This is one group and this is another group. Now here a weak electrostatic force of attraction is present between the hydrogen of OH group and oxygen of CHO group. This type of hydrogen bond is said to be intramolecular hydrogen bond. Intramolecular hydrogen bond. We have one compound known as nitrophenol. We have two types of nitrophenols. This means this is phenol group. If phenol group is present in ortho position, you will have NO2 group here and OH group here. Here you will have intramolecular hydrogen bond. There is another nitrophenol where you will have nitro group at para position. Nitro group is present in the para position. Now here oxygen, this oxygen and hydrogen are far away from each other. In such cases, this type of intramolecular hydrogen bond is not possible. That's why in para-nitrophenol, we can observe the formation of intermolecular hydrogen bond. Intermolecular hydrogen. Because of this intermolecular hydrogen bond, the boiling points of para-nitrophenol is more than the boiling point of orthonitrophenol. In orthonitrophenol, intramolecular hydrogen bond is there. So there will be no bonds between molecule and other molecule. When the bonds are present in molecule into other molecule, intermolecular hydrogen bonds are there. In such cases, their boiling and melting points are very high. Particularly here, the boiling point of para-nitrophenol is greater than orthonitrophenol because of that intermolecular hydrogen bond. In the same case, in H2O also, both H2O and H2S belongs to hydrides of same oxygen sulfur family. H2S is obtained in gaseous state, whereas H2O is obtained in liquid state because there is an intermolecular hydrogen bond in H2O, where it is absent in H2S. Another interesting question they may ask frequently in the examinations, both in board and competitive examinations. We can find intermolecular hydrogen bonds in hydrogen fluoride. So in HF molecule, this is one HF molecule, this is another HF molecule, this is some other HF molecule, like that. So here we will have partial negative charge, here you will have partial positive charge, partial negative, partial positive, partial negative, partial positive, partial negative, and so on. So now the partial negatively charged fluorine will attract with partially positively charged hydrogen, such that a strong hydrogen bond is present in HF also. These hydrogen bonds are stronger than the hydrogen bonds that were present in H2O. But H2O boiling point is 100, whereas the HF boiling point is less than 20 degrees. It is only 19.8 degrees centigrade. This is an interesting question. Because in the case of H2O and H2S, we claimed that the boiling point of H2O is more because of the intermolecular hydrogen bond. Here in HF, we have more stronger intermolecular hydrogen bonds, but still its boiling point is 19.8. Why? Here in the case of HF, no doubt the hydrogen bonds are stronger than H2O, but here in H2O, hydrogen bonds exist only when it is in liquid state. In vapor state, in H2O molecules, there is no hydrogen bonds. Whereas in the case of HF, hydrogen bonds are present in vapor state of HF also. So HF has hydrogen bonds in vapor state as well as in liquid state. So in case of HF, there is no need of breaking all hydrogen bonds that were present in the given amount of HF. Breaking a few hydrogen bonds is sufficient enough to convert into vapor state, because still in vapor state, hydrogen bonds are in existence. So the bonds to be broken to convert into vapor is less in HF when compared to H2O. That's why its boiling point is very less, that is 19.8. These are the three questions. One is why orthonitrophenol will have less boiling point than paranitrophenol. Another question is H2O boiling point is 100 degrees centigrade, whereas the same group hydride H2S is in gaseous state. Why? Next, third type of question, this one. Both HF and H2 are having hydrogen bonds, but boiling point of H2O is 100 degrees centigrade, whereas the boiling point of HF is only 19.8. Give reason. H2O can form hydrogen bonds only in liquid state. In vapor state, it cannot form hydrogen bonds. So to convert H2O into vapor, we have to break each and every hydrogen bond that was present in H2O. Another important point is, at an average, H2O molecule can form 2 hydrogen bonds, whereas HF can form only 1 hydrogen bond. So the number of hydrogen bonds to be broke or to be break to convert into vapor is very less when compared to H2O. That's why its boiling point is less. And another important question is, why acetic acid exists as a dimer? In acetic acid formula is CH3COOH. Its structure will be like this, COOH. Now another H2O molecule, this structure is COOH. Now CH3COOH. So there will be a hydrogen bond between oxygen of one C double bond oxygen with hydrogen, OH hydrogen, and another one here. Because of those 2 hydrogen bonds, 2 acetic acid molecules will exist as dimers. So these are the important points regarding hydrogen bond. The nature of hydrogen bond is electrostatic force of attraction. It is stronger than other van der Waals forces of attractions, but weaker than covalent bonds.